Hello, welcome everyone. I am Dr. Mrs. Shaila Dinkar Apte. I have published a book on signals and systems by Cambridge University Press. Here I am trying to generate the videos for the benefit of the students in order to understand basic concepts. So here we go. Firstly, let us define a signal. So what is a signal? Any particular quantity, physical quantity which carries some information will be called as a signal. That is any physical quantity which varies with one or more independent variables will be called as a signal. So the signal can vary with respect to time, signal can vary with respect to frequency, signal can vary with respect to spatial domain, and so on. So our speech signal, then any image that is formed, or the ECG signal, EEG signal, earthquake signal, all these are signals. So let us see how we can classify these signals. Analog signals, as we know, as they are generated in the universe, or suppose you consider the speech signal, it is generated as amplitude with respect to time, and it is continuously varying with time. It is having continuous amplitude as well. Then we have discrete time signal. Now, when we want to interface this signal to our computer, we would like to process only finite samples rather than infinite samples. So, in order to make the number of samples limited, what we do is we discretize the time axis and we convert it into a discrete time signal. Here, the amplitude axis will remain continuous. And then finally, in order to process it in the digital computer, we digitize it. In this case, we digitize both the time and amplitude axis. So time axis is discretized and amplitude axis is also discretized. So let us see what is the time domain signal. So what we call it as a domain is, domain means it is the name of the x-axis with respect to which we are plotting the signal. So in this particular case, this is the analog plot of the speech utterance, wherein amplitude is plotted on y-axis and x-axis is time. So as time varies, how the amplitude of the signal varies is plotted, and this is called as the time domain signal. So domain means the name of the x-axis, you can say. Now, this is a discrete time domain signal. Discrete time domain means the time axis is discretized or digitized. So, here what we do is, from the signal we take the samples at regular intervals of time. So, regular intervals of time means the distance between every two samples is fixed, and this particular t, capital T, that is the time period between the samples, is equal to 1 upon the sampling frequency, and this particular t is maintained constant. So then it is called as uniform sampling, because the distance between every two samples is uniformly maintained as a constant value. So in this particular case, the time axis is discretized. So the samples are taken only at particular values of time at regular interval. This does not mean that in between the two samples the signal is zero. Simply the signal is undefined for in between samples. Only at the sample position it is defined. So let us define what is the sampling theorem. Sampling theorem says that any energy signal which is band limited with bandwidth of W, sampled using the sampling frequency greater than or equal to 2W, then it is possible to reconstruct the signal from the signal sample. So when we discretize the signal, there is a requirement that we should be in a position to process it and get the analog signal back when it is required. In this particular case, when we are defining the W as the bandwidth, the signal will have to be always band limited. So the energy signal which is band limited, then only we can sample it and generate the discrete time signal. If the corresponding signal he is having infinite bandwidth, then how we define the sampling frequency? It is twice the W. So it cannot be defined. So in that case, the signal cannot be sampled. So remember that In order that the sampling takes place, we must have the energy signal which is band limited. So it must have some finite bandwidth equal to W. Then I can use the sampling rate greater than or equal to 2W. This 2W will be called as Nyquist rate of sampling. So here we consider a signal which is of 10 hertz. This is a 10 hertz sine wave signal, pure sine wave signal. Now I sample it at regular time interval. Here T is capital T is defined as 0.001. That means I am sampling at 100 hertz. So when a 10 hertz signal is sampled using 100 hertz as sampling frequency, the sampling frequency is equal to 10 times the W. So in this case, the recovery must be possible. So here I generate the signal samples. So these signal samples are there. I have considered one complete cycle of the signal. In one complete cycle, I have obtained 10 different samples from the signal. Now let us see. In time domain, what I have done? I have multiplied the signal by the train of impulse because I have taken the samples at regular intervals. Now, what happens in transform domain? When time domain it is multiplication, in transform domain it is a convolution. So, I'll have to take the Fourier transform of the signal, Fourier transform of the impulse train, and then I will have to convolve the two. So, for train hertz signal, which is a pure sine wave, the Fourier transform is just the 10 hertz line, the line at 10 hertz, the line at minus 10 hertz. This minus 10 hertz is plotted for convenience. We'll see the significance of this later on in the next chapter. Now, this is the Fourier transform for 100 hertz sampling, what you call it as the train of impulse. So, the line will be appearing at 100 hertz because it is a pure 100 hertz signal. Now, when we convolve these two, what happens is there will be repeated pattern obtained at 0, then 100 hertz, minus 100 hertz, then minus 200 hertz, minus 300 hertz, and so on. So, it will be infinitely repeated. Now, what I should do? Now, I'll have to isolate the signal spectrum. Now, when I isolate, I will take the multiplication of this spectrum with the rectangular pulse, or this rectangular pulse is of width equal to, total width is equal to 100 hertz, but it is existing between 0 to 50 hertz basically. Why 50 hertz? Because sampling frequency is 100 hertz. So the spectrum will be available only up to 50 hertz. So remember this, if you sample at 100 hertz, you will have information available only at 50 hertz, right? That is W, that is the bandwidth of the signal. So here when we just isolate the spectrum, we get the spectrum only between 10 hertz to minus 10 hertz, and there is no aliasing. If there is only 10 hertz signal, it can be directly isolated using this rectangular pulse. So there is a direct recovery of the signal that is possible. Now how we recover it? We take the signal samples, and at every sample we have to generate this sinc function. This sinc function is being used as the interpolation function. Sinc function is defined as sine pi omega 0 t divided by pi omega 0 c. So this is the definition of the sinc function, and this sinc function will be utilized at every signal sample that is recovered to generate or synthesize the original signal. So this is the recovery of the signal shown. These are the signal samples, those are obtained. Then what I do is I generate the corresponding sinc function on either side for every particular signal sample, and then I consider the resultant amplitude. The resultant amplitude is shown by this dotted line. So I am in a position to faithfully recover the signal. Why? Because I have used the sampling frequency which is sufficiently greater than the signal frequency. Now suppose we consider the signal that is sampled below the Nyquist rate. That means I am not obeying the Nyquist theorem. I am sampling below the Nyquist rate. Now this is a signal that is shown which is 90 hertz signal. That means in 1 second there are 9 cycles of the wave. Now I take the impulse train which is of 100 hertz, same as before. That means I am sampling it at 100 hertz. So with this impulse train, if I sample this 90 hertz signal, for these 9 cycles, I am getting only 10 samples. So hardly one sample per cycle I am getting. Now, do you think it is possible for you to recover the signal? If you just extrapolate these signal samples, those I have obtained, you will see that it is a very low frequency signal. That means this high frequency signal, that is 90 hertz, is now aliased as the low frequency. This is what is called as aliasing, means higher frequency is misinterpreted, or you can say it is misrecovered at the receiver end as a low frequency. So this is what happens when you sample below the Nyquist rate. So this is 90 hertz signal. Now when I take the convolution of these two spectra, what I will get is there will be the spectrum. See this 90 hertz. I will get the spectrum only between minus 50 hertz to plus 50 hertz. Now this 90 hertz will be aliased as 10 hertz. Now this we will see in the next picture very clearly. So just wait if you have not understood this. Okay, so this is the picture which shows how the analog frequency is converted into the digital frequency. So always remember that the maximum value of the digital frequency is equal to half, always. So whatever sampling frequency you take, that is the analog frequency, is converted now into the digital frequency. Fs is the sampling frequency. So suppose Fs is equal to 100 hertz, the maximum digital frequency that I get is 1 by 2 for the analog frequency of 50 hertz. So I can get the spectrum as the linear conversion between the analog and the digital value only from 0 to 50 hertz. Above 50 hertz, what will happen? Above 50 hertz, it will be aliased. How it is aliased, we will see it shortly. Here you see the phase spectrum. Here you will find that only between 0 to Fs by 2, only between 0 to 50 hertz, the corresponding phase is 0. But after Fs by 2, that is after 50 hertz, the phase is negative. So if you consider 90 hertz, this 90 hertz comes in this particular Fs by 2 to Fs range. That means in this case, the phase reversal will occur. And this 90 hertz will be aliased as 10 hertz. Just see how it is there. See, this is called as fold back effect for aliasing. See here, this is 10 hertz, this is 50 hertz. As I said, 50 hertz will be converted to maximum digital frequency of half. Now see, this is 90 hertz. This 90 hertz will be misinterpreted as 10 hertz. Why? Because it is as if we are folding this particular paper at this vertical line at 50 hertz. So when you fold back, what will happen is this 100 will coincide with 0, and this particular line will coincide with this particular line. So you will get a linear variation between analog and digital frequency when this particular line folds back onto the original line. This line will also fold back onto this line. This line will also fold back onto this line. So all frequencies on either side will fold back and will appear between 0 to 50 hertz only because you have used 100 hertz as sampling frequency. This is what is called as aliasing. So all frequencies above 100 hertz, above 50 hertz, all will be aliased. And what will be the phase? The phase will be depending upon whether it is on this particular range, that is between 50 hertz to 100 hertz, then again between this 100, then 150 to 200 hertz. So all this will be aliased, and it will have a frequency folded back, and the phase will also be reversed in that case. I hope you have understood what is aliasing now. So always remember that the sampling frequency will have to be greater than or equal to 2W if W is the bandwidth. And when you sample at Fs that is equal to 2W, you will have information available only up to W. Or in other words, because you have information only up to W, you have sampled at 2W. And when you sample at 2W, you will have information available only at W, only up to W. So let us consider one analytical example to make it very, very clear. So consider the analog signal represented by this particular equation. Xt is equal to 3 times cos of 50 pi t plus 2 sin 300 pi t minus 4 cos 100 pi t. Now what is the Nyquist rate for the signal? If the signal is sampled with sampling frequency of 200 Hz, what will be the discrete time signal obtained after sampling? What will be the recovered signal? So this is the question. Now we'll have to, from this signal, we'll have to find out what are the frequencies in this signal in order to find out what is the bandwidth. Right. So this is 50 pi t. Now compare it with 2 pi ft. If I compare this 50 pi t to 2 pi ft, I understand that frequency is 25 Hz. 300 pi t, if I compare it with 2 pi ft, this corresponding frequency is 150 Hz, and here it is 50 Hz. So 25 Hz, 150 Hz and 50 Hz. So maximum frequency is 150 Hz. So bandwidth is 150 Hz. So I will have to sample at 300 Hz. But now what they are saying, the signal is sampled at 200 Hz. So we'll have to see what happens when you sample it at 200 Hz. Okay. So let us see. So what I do is I put t is equal to n into capital T in order to digitize it or discretize it. So I get xn is equal to 3 cos 50 n pi by n pi into capital T. But what is capital T is 1 upon fs. Here fs is 200. So 1 upon 200 plus twice sine 300 n pi upon 200 minus 4 cos 100 n pi upon 200 on similar lines. Now this 50 n pi upon 200 is nothing but n pi by 4. This is 3 n pi by 2 and this is n pi by 2. Now we have to consider what will be the recovered signal. Now this 3 n pi by 2 can be written as n pi plus n pi by 2. Right. So I will write it as n pi plus n pi by 2. But what is n pi plus n pi by 2? Sine of that is just minus twice sine n pi by 2 because it is pi plus angle. So it becomes negative. So in this case, the phase reversal occurs. You see, this is 3 cos n pi by 4, same as before, minus twice sine n pi by 2. Now this becomes, and minus 4 cos n pi by 2. So the signal has three digital frequencies. What are these? The first one is n 2 pi n f1, where f1 is the digital frequency, is equal to n pi by 4. So if you compare what is f1, it is equal to 1 by 8. Similarly, f2 is equal to 1 by 4 with a negative phase, and f3 is equal to 1 by 4. Right. Now f1 is equal to 1 upon 8. So 1 upon 8 of what? 1 upon 8 of 100 Hertz. Sorry, 200 Hertz, because 200 Hertz is the sampling. So what will be the frequency? This is 25 Hertz, same as before. This becomes 1 by 4. 1 by 4 means it becomes 50 Hertz with a negative phase. And the third one was 50 Hertz, which is recovered as 50 Hertz. So now see here. Now from this picture, it will be very clear to you. See, 25 Hertz means it is on this linear scale. So this 25 Hertz will be recovered as 25 Hertz only. No problem. 150 Hertz will be aliased. This line will drop onto this line and 150 Hertz will be aliased as 50 Hertz. But what will be the phase? The phase will be negative. So it is recovered as 50 Hertz with negative phase, and 50 Hertz remains as it is with same phase. So this is how the signal is recovered. I hope you have understood. So always you remember the digital frequency will be having maximum equal to half, and this lower figure indicates the phase. So between this linear, basic linear range between 0 to fs by 2, it is a linear range. It has phase equal to 0, and for all other things it will fold back onto the same range, and if it is between 100 to 200 it will have phase negative. Again 200 to 300 it will have positive phase, 300 to 400 again it will have negative phase, and so on. Right. So now consider one more example. In this case, xt is cos of 1 pi 150 pi t plus 2 sine 300 pi t minus 400 cos of 600 pi t. So what are the signals? Here 75 hertz, here 150 hertz, and here 300 hertz. So what is Nyquist rate? Nyquist rate will have to be twice the W. That means it should be 2 times 300, so it is equal to 600 hertz. So this is simple example. Now here the third example says design anti-aliasing filter for a signal represented by this. Now here again we first find the frequencies. This is 85 hertz, 95 hertz, and this is 125 hertz. So the required sampling frequency is twice this 125, so it must be equal to 250 hertz. Now, what is anti-aliasing? Anti-aliasing means you want to avoid the aliasing. When the aliasing will be avoided? Aliasing will be avoided only if you allow the frequencies up to W to pass through. What is W here? W is 125 hertz. So, allow only the frequencies up to 125 hertz to pass through. Other higher frequencies will be just uh, means will all these frequencies will be cut. So you need to design a low pass filter with cutoff frequency of 125 hertz. This low pass filter with a cutoff frequency of 125 hertz will then be called as the anti-aliasing filter. Thanks for patient listening. We will